All right, so Intro, Chapter 3, Section 5 is about ionic compounds, and more specifically, it's about naming ionic compounds. Looking at my text right here, it's called, what's it called? Formulas and names, okay? Formulas and names. And we're going to find that there's three different kinds. They're the easy ones, there are the hard ones, and there are the ones that are more difficult yet. Okay, so first of all, let's I don't know, go back and think about some things that probably should be obvious. First of all, ionic compounds always contain both positive and negative ions, right? Always contain both positive and negative ions. Of course, they've got to be electrically neutral. In a chemical formula, the sum of the charges of the positive ions, and what is the name of positive ions again? Say it out loud. Cations, right, must equal the sum of the charges of the negative anions. And what are the negative anions? And negative ions, anions. Okay. So in a chemical formula, the sum of the charges of the positive ions have got to equal the sum of the charges of the anions. Okay. The formula reflects the smallest whole number ratio of the two. Got a phone call here. Patrick?
Yeah.
I'm doing a video.
Okay, go ahead. Sorry about that.
Got an emergency?
No.
Okay, talk to you soon.
Bye.
Bye-bye. The formula reflects the smallest whole number ratio of anions. That'll make more sense as time goes on. Okay, so in other words, I guess you might want to point out that these are always going to be... Can you read my writing? Empirical formulas. Okay, so let's look at the first kind. Actually, before we do that, let me point out that this video really stinks. Okay, Intro, Chapter 3, Section 5. Ionic compounds, and more specifically, we're going to be looking at formulas of ionic compounds and naming ionic compounds. And we're going to find that there's some easy ones and some that are not easy and some that are worse than not easy. Okay, so let's start out by reviewing some things that probably should be obvious. Ionic compounds always contain both positive ions and negative ions, right? In a chemical formula, the sum of the charges of the positive ions, what's the name of the positive ions? What do we call this again? Remember this pen color? Let's go to a different color, black. Cations, remember that? Let's go back to our other color. Must equal the sum of the charges of the negative ions. And what's negative ions called again? Say it out loud. Anions. Very good. Okay. So in a chemical formula, the sum of the charges of the positives have got to equal the sum of the charges of the negatives. Why? Because it has to be neutral, or else you are going to get a lightning bolt. That's a terrible lightning bolt. Here, let me try that again. Right? That's what you get when you do not have neutral charges. You get lightning bolts. Okay. So the formula reflects the smallest whole number ratio of ions. And that sounds like an empirical formula, doesn't it? It's the smallest whole number ratio of the ions. Okay, that'll mean more as we get into this. Okay, so before we move on, let me remind you about how we get ions, or rather how we can know, based upon looking at the periodic table, what the charge of ions are. So you may remember that the rule that that nonmetals over here have a tendency to take electrons. They have a tendency to become anions, and metals, which are here, have a tendency to take on positive charges, right? Because they donate electrons. You may remember that. All right, now, did you also remember from page, I think it's 60, page 60, that these guys, main group metals, have a tendency to donate electrons such that they become cations with the same number of electrons as the nearest noble gas. Okay, go to page 60 and look at that. Actually, I've got a slide here that's going to remind you of that. Okay, so that means that this is going to take on a +1 charge, right? It'll lose an electron. Potassium, for example, will lose 1 electron and have the same number of electrons as argon. Potassium and argon have the same number of electrons. Sodium will have a tendency to lose 1 electron and have the same number of electrons as neon, right? Can you see that? That's the closest one. Sodium starts out with 11 electrons, but then when it loses an electron and becomes positively charged, it has 10 electrons left, right? Okay. And these guys, these main group elements, will have a tendency to gain electrons and have the same number of electrons as the closest one. So anyway, that's a lot of information, but you've seen it before. Just reviewing it. It's on page 60. Let's look at the rules as they show up on page 60. You'd really be better off opening up your book, or rather, you'd be better off guessing, right? Remember this? A main group metal tends to lose or gain electrons. It's a metal, right? So what is it? Tend to gain or lose? It tends to lose electrons because it's a metal, right? And forming a cation plus, right? Forming a cation with the same number of electrons as the nearest what? Noble gas, right? Which we reviewed in the previous slide. A main group nonmetal has a tendency to what? Gain electrons. Oops, that's wrong. Forming an anion with the same number of electrons as the nearest noble gas. And then a non-main group metal generally tends to lose electrons. Tends to lose electrons with has a tendency to lose fill in the blank here. Pause the video. Go look on page 88. Page 88. And tell me what word goes here. Okay, I'm going to suppose that you paused the video, and I'm going to say the word is variable. A variable number of electrons. In other words, a non-main group metal might lose 1, it might lose 2, it might lose 3. They take on different charges. We'll see more what that means in the next few slides. Okay, so we're supposed to now, for example, 3.3, this is on page 87. Write the formula of an ionic compound that forms between aluminum and oxygen. All right, so every time you see something like this, you really should pull out your tools. So I'm going to pull out the periodic table, which we showed just recently. Write the formula for the ionic compound that forms between aluminum and oxygen. Right, so aluminum is going to have a tendency to take on a +3 charge. Oh, I didn't point that out in the previous one, right? There are actually 3 transition metals that have, 4, that have predictable charges. Aluminum, 2, or rather 3, 2, and 1. Look at that, 3, 2, and 1. And scandium, which is 3. So you can memorize those. You're going to need to memorize those. 3, 2, and 1, and 3. These, we always know what those charges are going to be. So if aluminum is going to take on a +3 charge, 1, 2, 3 plus signs, and oxygen is going to take on what? What's oxygen going to take on? This is going to be 0, -1, -2. This group has a tendency to take on -1, right? Become like neon. Oxygen is going to have a tendency to take 2 electrons to become like neon. Okay. All right, so if these guys are going to form, back to the first rule on the previous slide, the very first rule on the of course slide is that these charges are going to have to equal each other in order to make a neutral compound, right? So what's this going to give us? This is plus 3, and that's minus 2. What's the lowest common multiple of those two? It's going to be aluminum 2, oxygen 3, right? Because 2 times 3 is equal to 6, and over here 3 times 2 is equal to 6, right? We have to have a total equal number of charge between the two of them, all right? So it's Al2O3, aluminum oxide, Al2O3. All right, let's look at another example, calcium and oxygen. So again, pull out your tool, periodic table, and calcium is here. Has a tendency to take on a plus 2, right? You knew that. And oxygen has a tendency to take on a minus 2, right? Okay. So what's the lowest common multiple of plus 2 and minus 2? Well, it's just 2, right? So that's going to be CaO. Can you see that? All right. Now, for the not so easy problems, or not so easy naming compounds. So first of all, if you're going to name these guys, the ones that have predictable charges, which are all in color here. Do you see that? This is too small to read, I know. I'm just showing it back in front of you because it ought to be familiar to you by now, or it's going to be familiar as you look at it more and more. So the ones that are colored are predictable. Aluminum, zinc, and silver, which I know you can't see from where you're sitting, but pull it back out. It's on your book on page 84. Okay? Aluminum, zinc, and silver, scandium, and then it's the main group metals, right? Okay, so the name of the cation plus the name of the anion, and you put "ide" at the bottom, okay? Now, if it's not one of those colored ones, then you don't know what the charge is going to be. Copper, for example, takes on a plus 1 and a plus 2. Iron takes on a plus 2 and a plus 3. How do we know that? Well, we look it up. That's how we know. So, the name of the cation and the metal, if it's colored, that's type 1. And then if it's not colored, we got to say what the charge is on the other one. Let me give you an example here. Let's take one of these colored ones. Let's say calcium. Okay? And let's take a non-metal with it. Let's take that, chlorine, right? So what charge is calcium going to take? It's going to take a plus 2. What charge is chlorine going to take? Well, it's in this column here, right? So it's going to be a minus 1. Well, how can I make these two numbers equal, these two charges balance each other out? It's going to require two chlorines, isn't it? CaCl2. Okay, so now I'm going to ask you to name that. And the name of that is going to be name of the cation, which is calcium. And the base name of the nonmetal, which is chlorine. And we'll put "ide" at the bottom. The base name is chlor, right? It's calcium chloride. All right. Now, if we have one that we don't know the charge of, let's say iron. Let's say FeCl3. Now, I mean, right, you wouldn't know it unless you got the formula. We know what it is now, right? Because there's 3 minus 1s here, so it's going to be minus, minus, minus. How many pluses are going to have to be in iron to make this neutral? Well, 3. 1, 2, and 3. Can you see 3 plus signs right there? All right. Now, if you see iron's right here, okay? You see it's not colored, and so the name of the cation is iron. But since it's not colored, we're going to have to put the charge of it there in Roman numerals. And what's the charge? It's 3 plus 3. 1, 2, 3. And then the base name, which is chlor, and then ide. Chloride. Okay? So that's the name of FeCl3, is iron 3 chloride. All right, now let's do another one. Naming ionic compounds containing a metal that forms only one type of cation. All right, I know we already did an example like this, but we're going to do it anyways. The name of the cation, remember, because it's, where are we? Calcium. There's calcium right here. And calcium is right here. Right, there's the main group. Remember this? Transition metals, okay. So the first thing we're going to do is we're going to say calcium. Calcium, and then the base name of the anion, which is bromine or brome. It's brome because it's the base name, right? And then ide. Calcium bromide. All right. You already got it. There's the base name. Base name. I know you already got this, but I just want to point it out. And there's your ide, right? And there's the name of the cation. Okay. Where are we here? Where are we? I gotta. Okay, naming ions that form. Naming ionic compounds containing a metal that forms more than one kind of cation, right? So lead. Well, lead was in the periodic table. Probably should have kept it out. Lead's right here, right? Transition metal. So we don't know what charge lead takes. We know from the formula here, because there's 4 minuses here, right? And if this is neutral, this is going to be 4 pluses. So this looks like this is going to be, the name of the cation is lead. And then we're going to have to put Roman numerals because it's not main group or aluminum, zinc, or silver, or scandium. It's none of those. So it's got to be variable. And so we'll say lead 4, the base name of the anion, which is chlor, and then ide. Lead 4 chloride. Okay. All right, let's move on. Now we need to name, now we're going to go to the hardest ones. But before I do, okay, so I need to introduce polyatomic ions to you. And it's important, I think, to appreciate with polyatomic ions that, first of all, there's a bunch of them here, right? There's a good 20 of them here. But it's important to appreciate that in the beginning, you don't really need to understand why they're called what they're called. Just you need to practice them as they are. So you need to pull this table out. This table's on page 91, and you need to use it very faithfully in the beginning of your practice. Okay? So having said that, I'm going to ask you to sort of turn off the questioner in your head, like why, and I'm going to ask you to simply believe me that this is called acetate. You see that? C2H3O2 minus, that's acetate. CO3 2 minus, that's carbonate. Bicarbonate or hydrogen carbonate. Hydroxide. Nitrite. Nitrate. Okay? So again, don't in the beginning you just need to sort of pull this table out and assume that you know those names. Pretend like you know those while you're practicing, and you'll find after you practice them a good bit that they become far more comfortable. See, these are polyatomic ions, and now we're going to have to name ionic compounds that have a polyatomic ion in them. Okay, so let's look at an example. We're going to do it just like we did with the other one, except this time we're going to replace the anion name that we were using before with an anion here. By the way, there is one cation here in this list, and only one, and it's ammonium. Okay, so obviously we won't have many compounds that have ammonium in it, but they do exist. Okay, so let's go and look at this. First example, lithium 2 Cr2O7. All right, so we go back to that table, and we'll pull it out right now, and we'll pull out the periodic table also, and we find that lithium is right here. Okay. So we're naming this. We name the cation first, and it's colored, right? It's always a +1, so we don't need to say what its charge is. And then we go to the Cr2O7. Now, Cr2O7, again, I'm going to ask you to pretend like you know this, so you have to scan through this list and look for it. It's right there, and it's dichromate. You see that? What's the charge on dichromate? 2 minus? And what's the charge in this? This is 2 minus. And what's the charge in lithium? Plus, but there's 2 of them, right? So these things match. Dichromate is Cr2O7 minus minus, and lithium is plus, and so there's got to be 2 of those. All right, so it's lithium dichromate is the name of that compound.